So, this is the question. What is the null potency class of S3? Okay, so if we try, you know, for abelian group is 1, right? Because that's the shortest series. All right, E and G. You have this is true. You can have any H inside if G is not trivial, but we can check this last time, right? Because this is equal to G. And this is also. You see, if this is always G, let me write this. Okay. This is always G. This is always G. So for any group, if the center is the whole group, then this is true, right? For the central series. Okay. Now, if you say that the negative class of S3 is 1, how do you show it? Shiham, you have the working. You just say 1, but there's no proof it's 1. Anyone has the reasoning why? Yeah. Anyone want to say it? No one?
Is it because it has no center?
You have said the nepotistic class of S3 is 1.
Because it has no center.
It is not 1.
I think proof the based on my understanding, the nilpotency class is 2.
Hassan,
It's
are
not
you
1.
talking or what?
Yes. Based on my understanding,
No,
the nilpotency class of
if you
S3
say, I
is
just give the answer
2.
here, right?
Yeah.
If you say this is the shortest one,
Hmm.
then you need to prove that right? And what is the center of S3? This is, what is the center of S3?
S3 doesn't have center.
S3 is not abelian.
It has no center.
The center of
Anyone?
S3, the center of S3
Hassan,
is the identity.
I thought you were talking, but I cannot hear anything from you.
Prof,
You see?
Prof, can you hear me?
Hassan is talking.
Prof,
Because there's no microphone. Hassan.
Prof, can you hear me now?
Okay. My volume is too slow. Okay.
Prof, is it because S3 has no center?
What is the center of S3?
The center of S3 is the identity element, 1.
The center is 1. So is this right?
No.
It's not right.
Yes.
So, Shiham, this cannot be the central series. The next one you try, normally what we do, the easiest one is you put a center there. If the center is this, you put something normal. But this doesn't work, right? What is the normal one? This, right? Okay, try this. So you have to check twice, right? You have to check. This. This. Is that right? The other one is the same thing, right? Is that right? By definition of the central series. Where's my
I think this right, Prof. This isomorphic to side 2, yeah? The first one and the second.
okay? So this is order 6. This is order
3.
3. So this is isomorphic to
Side 2.
Z2. What about this? Also, right?
This one also. Also, yes.
This one also. This is okay. What about the above one?
The first one does not satisfy this condition.
This one is okay. This one is not okay.
Yes.
Right? Because this one is 1, 2, 3. is not a subgroup of center of S3 is 1. Okay, so what can you conclude?
We conclude that this group does not have any nilpotency class.
It's not nilpotent.
Yes.
Oh. That is what you said. I still put a question mark because some of you probably have not tried and look whether it's nilpotent or not for S3. Any others? Did you look? Like any reference? What happened with S3? Hassan, where did you look?
I didn't look, I just
You just think. To double check, okay? Because you try, that's the only way, right? For S3, S3 only has that possibility of subnormal series or normal series, right? Because to have the central series, you have to have a normal series. So the only normal series would be that, the one that I shared, but that is not central series. The other one is the trivial one, right? The trivial one, you cannot show that it is a central series, right? So in conclusion, it's not nilpotent. The next is about D4. Did I do D4 last time?
D4 is the assignment.
Oh, is it the assignment? Oh, assignment, D4 and Q. Okay. As an exercise. So I have to edit this button. I think this one is for the billion. Okay, can anyone show me for D4 and for Q? Anyone want to share? Or let me make this quiet. Okay. Okay. Farah, do you have something to show?
Yes.
Can you share it?
Prof, actually I have two of it, but I'm not sure which one is correct. Like the S3 case, you have to prove it too, but one of it I can prove it, but the other one something is not right. But I'm just gonna show you the first one, the whole thing.
Okay. So you're using the center, yeah?
Yeah.
So using the center, that's the easiest way actually to use the center because it's always normal. The center is always normal. Okay. So to show its upper central series, you have to show two parts. Okay? Two parts. The first one is R180 mod R. This is, what is it? Center, right? Right? So this one is isomorphic to R180. So equal, yeah? This one is, oops, isomorphic to Z of D4, which is R180. So this, so it's okay. The second one is?
The second one is actually this one, but I don't really understand this part because.
Okay, let me finish this because this is not finished yet. Okay, so this one, this is isomorphic to something of order 4, right? Something of order 4. You have to check which one. It's either this or this. And this is the center. If I can actually show whether this is this or this. But either one, this is a billion, right? Suppose it's this. This is a billion. So if it's the same thing, the center of that will be that because it's a billion. So they're equal. If it's your job to see which one. If it's this, then it's a billion, the center is this also, so they're equal. How do you find whether it's this or this? You have to figure out in the coset, right? You see if the coset has order 2 or 4. If there is no coset of order 4, then it's this. If there is a coset of order 4, then it's this. So this is to show that D4 is nilpotent of class. Your second one is which one? Where is your second one?
This one. I think it's a bit weird there because I don't understand that part. I don't get that part.
Oh, this, okay. This is the one I just explained, right?
I cannot see because I'm sharing my.
Stop sharing.
Oh, stop sharing. Okay.
Okay. This is the part that you're not sure, you said, right?
Mm-hmm.
Okay, so you have D4 over this.
Mm-hmm.
This is a factor group. So the elements are coset. We know this is order this is order 8, this is order 2. So you know this is order 4. Any group of order 4, it's either cyclic of order 4 or isomorphic to climb 4 group. Okay, which is both a billion. You cannot say this is some subgroup of this is just isomorphic to whatever group of order 4. In each case, they are a billion. So the center of this, if it is this, center of a billion group is this. If it is this, the center is also this. Okay, to know whether it is this or this, you have to figure out the coset.
Prof, that means I have to always check the isomorphic to something instead of I just depends on the coset, is it?
If you find the coset, then how do you show that this matches or subgroup of this one?
So I have to check what isomorphic to something that's better. Okay, I see. Easier. Okay, Prof. Thank you, Prof.
Okay. It's good to have this as a next assignment, right? So I can really see, write it out. The answer is already there. Just how you write it out. Or maybe I give you the first test, right? Yeah, it is in the exercise. Okay, so right. Another one is Q. Can somebody else show for Q? Anyone? Anyone want to share? No one? You just follow. What is the?
Yeah, okay, Prof. Yes.
Okay.
But I just put this isomorphic to Z4. It can be, yeah.
Yeah.
Four.
You're not sure whether it's Z4 or Z2.
Yeah, yeah.
It is very similar. This one is very similar to the hetero, right? Just now. If you just choose the identity, and this is the center, right? The easiest way is the trivial one, the center. You try that first, and then the group, right? Quaternion. The center is one and negative one, the only one commute with the rest. So you check, right? Whether this is, oops. Okay, so this is just this, which is Z2, right? This is the same thing, right? It's the same. This is isomorphic, but this one is equal, right? So this is okay. Second one is this, right? Q. Q. Okay. So this is order 2, order 8. Again, this is order 4. Okay, Hassan, you can stop sharing.
Okay.
Then you cannot see this. So, well, actually, there is a way to see while sharing. This is complicated. 8, 4, right? So something of order 4. If you write this with explanation, I can accept, right? And this is the center of the same thing, right? I can put this H. H is Z4 or which is equal to H, right? Okay. So they are equal. Do you want to see how do we decide H? Yes or no? Yes. Okay, now we go back to chapter 8 from last semester, normal subgroup. Okay, now what is Q mod is? Okay. Q equal -1, 1, -I, -J, J, -K, K. Right? -1 equal -1, 1. Okay. You want to find the left coset, right? Okay. We call this H, right? Okay, so this is equal to negative H also, right? Okay, negative 1 times H, negative 1 times H. So we can say this. Now we multiply I times H. You got I, negative I, or negative I, right? Which is negative I, H. You see, now I think you probably remember this, so you can solve it. Then you also have JH and KH. So you have 4 cosets, right? The number of cosets. Okay. Okay. Now, if you do this, H, I think we did this last time, right? Multiply. Okay. H times H is 1 times 1, right? This is 1 times. What is I times I? I squared is
Minus H.
negative 1, which is H. Negative H is H. Ij is K. Ik is negative J, which is J. Okay. Ji, Jj, Jk. Ki, Kj, Kk. Right? So you can see by the diagonal, what does it mean? What does it mean? It means all elements. I use all these. What? M. MH. MH is H. Right? So the order is 2 if M is not 1. K times K, KH times KH is H. So this is like saying X squared is E. The order of X is 2, except for the identity of order 1. So we have a group of order 4, which is isomorphic to what? Klein 4 group. Klein 4 group. Because now we have a group, we write like this. No. I can use this. So I can write Q for 21, or Q1 H, right? Is H, IH, JH, KH, which is isomorphic to, you see, is abelian, yeah? Okay. Okay or not okay? Where is the okay reaction? Okay. Clear, right? Even our thumb can be different color, yeah. One is more yellow than another one. Okay. All right, so that's why. Hassan, if you put Z4, that is wrong.
Yes.
Although the answer is right because it's a billion, we are safe, right?
Yeah.
Okay. Next is the next After this, the one that I will share again if you're interested. There is a sharing by alumni, UTM alumni from Yemen. He's sharing about his experience in UTM. So there's a Facebook Live after this at 4. Make sure you fill out the attendance, right? As your record. For PhD student or master student by research, by the end of before the end of the semester, you have to fill out your progress report. Even if you take dissertation, also, because it's the third semester, you have to fill out a progress report. So you can put the activity as one of the non-academic activity. Okay, that's sharing. Then that is a proof, because if you fill out the attendance form, you'll get the certificate, a certificate. So the sharing is from 4 to 5. So I will stop our class before that. Yeah. Last time we had from another country. The next one we'll have from, I think, Pakistan, our student also. The next one will be India. Oh, India first, then Pakistan. Okay. Maybe when after you graduate, we ask you to share. All right. So next is, what is it? Isomorphic series. Okay. Now, what is the definition of an two isomorphic series? So this time it can be subnormal or it can be normal. Two subnormal or normal series HI and KJ of the same group G. Of the same group G is isomorphic if there exists a one-to-one correspondence and between this collection of the factor group. Okay, not H to K, but the quotient of HI plus 1 to HI and KJ plus 1 to KJ. Okay, if there exists a one-to-one correspondence between the collections of factor group HI plus 1, 1 HI and KJ plus 1 to KJ such that the corresponding factor group is isomorphic to each other. So now in your mind, you'll be thinking about, oh, I have this one normal series and a subnormal series. I have two of them. Are they isomorphic? Okay. Then you will remember the drawings, the subgroup lattice that I draw last time. Okay, and check whether how these two can be isomorphic. Okay, let me start by examples. Easiest example will be abelian group because all subgroups are normal or subnormal series, right? Then we will see and find this factor groups. All right. So I give you an example for Z15. Okay, so if you remember, Z15 there's only 3 and 5, right? 3 times 1. And then, yeah, this. So you want to get the right number of the length, right? To match the isomorphism. If they have different length, then how can you match the isomorphism? So you choose the right length. Okay, so one would be this, right? Another one is this. Okay. So for the first one, you have this. Is actually isomorphic to just that one, right? That one is order 5, right? Okay, this is order 5. For the other one, Z15 3. 15 is 5. 15 over 5 is Z3. Okay, that is for the first one. For the second one, you have 5 over 0 is 3, right? And this is 3, so 15 times 5. So you see, you can take the corresponding here and here, and here and here. Okay, so they are isomorphic. So we have this isomorphic. There is a one-to-one corresponding. So you put phi. So it's like this. This one. If you really want to write this is equal to isomorphic to, right? Isomorphic to Z5, Z3. I better put the
Paragraph tu baca minum.
Hassan. I don't understand. He's talking in your language or
Yeah.
talking to me? Okay. What is it? I want to write the factor group, right? The factor group. I can write like this. You don't have to write this, but I just want to show in detail. Okay, which is isomorphic to Z5 and Z. Okay, so that is the collection of the factor group. For the other one, if I call it K, right? KJ. Okay, so this I will write this is Z3 and Z5. Okay, so my isomorphism is mapping this to this, right? And mapping no, I just put your voice. I've closed now. Z5, Z3, Z15. Okay, so this is what it means by mapping this. No, this is wrong. Balik ya. This one is. This is Z5 to this. Okay. Sorry. This to this. So this to this. Okay, now Z3. Z3 to Z. Okay. Okay. All right. After this, I won't write in detail what I just mentioned. Okay, let's try. One more. Let's try one more. We will try. What's the longer one that we did last time? Z12, right? Remember Z12? 2, 3, 6, 4. Is that right? If you take like this one is of order 2, 2. What's the order here? This to this is of order 2, right? Order 1, order 2, order 1, so it's 2. This one is order 4, order 2, so it's 2. This is 3 or 2, 3. This one is, this is order 6, 2, 2. This one is order, right? 4, 4 is 3. 3, right? 3. This one? This is order 2. This is order 3. 2. Hmm? 6. Yes. 2. 3. Okay. What is this? Right? Yes. Because we have to see the quotient, the order of the quotient. So it's easy to see this way. So you can choose 2 to 3 and 3 to 2. So that becomes isomorphic, right? So you can take okay, so here we have 2, 2, 3. Isomorphic 2. Okay. Okay. This is what just now 3, 2. So this is isomorphic to this, right? The quotient 3. This or this can do isomorphism also. Okay? So you do this one. If you take 2, 3, 2, still okay. Right? Still okay. As long as so you have this way, this way, this way. What about a shorter one? What about a shorter one? If you take 6 here, that will be 2 here. What is this? 2, right? What is the order of 6? 2, 6, right? Right? So if you take this, then you can take because this is right 2 times 3 or 3 times 2. So you can take this until here, then it is 6 and then 2. This is 6. Something like this. And many others, right? You can take okay, but I have a but. What about this? These two isomorphic. This one is 4, right? This one is okay. So you cannot. It's not. There is no isomorphism. So you can see the quotient have to have the same order because 2 groups that are isomorphic have to have the same order. Okay, enough on this. I can give you many others, but I think you got the idea, right? So there are many possibilities. I can give you any 2 subnormal or normal series of a group, and the question will be decide whether this is isomorphic or decide whether this is not isomorphic, right? Okay. So if the order is not the same, then you can say there is no isomorphism. It's not isomorphic. And if the order is the same, you have to have that isomorphism. So mapping this to this, 1 to 1 onto and prism operation. Okay. Next. Okay. Jordan holder. Yeah. Okay. Any 2 subnormal or normal series of a group G have an isomorphic refinement. 2 subnormal or normal series of G and isomorphic refinement. You know, if you understand, if you remember what refinement means you have a larger one, right? Larger one that cover up. It's the old one, the shorter one is contained in the longer one, refinement, right? So if we have, I erase. Just now, we have the shorter one, which is not isomorphic, right? But you can take a larger one. You let me erase this. You remember there's a long 2, 3, right? The series, normal series. And I've taken 2 short one, which is isomorphic, right? And then I show you one which is not isomorphic. So this means, although these 2 are not isomorphic, can you give me just now the one that is not isomorphic? I write again. 0, 3, right? And then Z12, right? The other one is 0, 6. Try just Z12, right? Because this one, 4, 3, 3. Okay. This one is
2, 6, 2, 6.
okay. See, they're not the same. But I can have the refinement, right? The refinement, which is bigger and will cover this and be isomorphic, which is the bigger one just now. The isomorphic bigger one. What is it? 6, 3, Z12. What about this one? Hmm? 6, 2. This is isomorphic? Is it?
Yes, because the same order.
Okay, so these 2 are called the isomorphic refinement. Okay, isomorphic refinement. Although this and this is not isomorphic, it's not isomorphic because of the 4, 3, 2, right? 2 or 6? 2, 6. Right? But this one is 2, this one is 3, this one is 2. Okay, this one is 2, 2, 3. Right? So 2, 3, 2, 2, 2, 3. So these 2 are isomorphic. Okay? So I'm not going to give the example there. You can read through, but there is another example. Okay? Okay. 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 I asked, I say okay. Okay, so the next definition is about composition series. Okay, composition series. Composition of subnormal series. this is a subnormal series. It's a composition series if all factor groups are simple. Okay. The subnormal series of a group G is a composition series if all factor groups are. What do you mean by simple? No proper, non-trivial, normal subgroup. And you have to remember about everything about simple groups, right? If a group is a billion, it is not simple. If it's cyclic, it is not simple because cyclic implies a billion. If the order is prime, then it is cyclic, then it's a billion, then it's not simple. So this is characteristic that you have to look. Okay. Next, we go to composition of normal series. So it's very similar to this. Instead of subnormal, we just do normal. Okay. But if it is normal, sometimes it's called principal, and some would call this chief. Okay. So there's a special name for composition of normal series. For a billion group, they are the same, right? Okay, now example. This is a group Sn okay. My very simple question. Why is An normal in Sn? Because the index is 2. The index is 2. Okay, so this is a normal series. What are the factor groups? So you look at this. This is isomorphic to An. And by that previous one, I mentioned that this is simple for n bigger or equal to 5. Okay. And for this is isomorphic to Z2, right? Which is but An. This is simple. Why? It's a billion, right? It's a billion. This is prime, right? So yes. Okay. Now, so this is true for this case. It's a principal series for this case, right? Now the last part of this, before I go to the group action, is on solvable group. Also, this I have mentioned in previous class. A group is solvable if there is a composition series and all factor groups are a billion. Okay, so you know if the factor groups is isomorphic to it is solvable if all of the factor group is abelian, meaning one of it is if it's isomorphic to an abelian group, right? Or isomorphic to a group G, a group K of order P, because it's always prime, billion, even if it's not P, like just now Z4, right? So if it's a bit, it's isomorphic to a group, a billion group, then we know that ZP or prime or cyclic, right? They're all billion. Okay, or it's the order is 4. So this is okay. Right? You can go through and look at the examples. Okay, now I want to start with a group action. Okay, you know binary operation, right? If you have a set, then a binary operation is an operation from a set to the same set or to another set that brings 2 elements to 1, right? So that is a binary operation. You can have from G to G and goes back to G. Okay. Okay. Give me an example of a binary operation. Everyone, each one, examples. I give one. Amtinan, you're next. Give me a set and an operation which is binary.
U8
U8
with multiplication.
multiplication modulo 8, right?
Yeah.
Okay, Farah?
S3 with
Composition. Okay, give me a set which is not necessarily a group. Hassan? No need to be a group, just any set with binary operation.
Okay. Z under multiplication.
Set of
Integers.
integers under multiplication.
Mm.
It's not a group, but
Yes.
it's a binary operation. Okay. Enough? Not a binary operation. Okay. Next is Ain.
I don't know, Prof. What do you mean by not a binary operation?
You take the binary operation of 2 elements in G. The resultant has to be also in G. That means binary operation. You take 2 elements in the set, you do the operation, it is back to be an element in the set. You take 2 integers and you add, you get integer, right? You take, this is a group, so this is cheating a little bit. This is also, because it's a group. That's why I asked for not a group. You take any integer, you multiply 2 integers, you get an integer, right? So I want you to give me a set in which you take 2 elements in the set, you do something, you don't get an element in that set.
Set of integer under division.
That's an example. You take 2 integers, you divide, you don't get an integer back. So it's not a binary operation. It goes out, right? Okay, Ayn, you want to
Prof.
try?
Yes, Prof. Matrix addition.
Matrix under
Addition.
addition.
Yes.
That is under binary, right?
No, because if not equal, row with the column cannot additive.
Meaning if it is the same n by
Yes.
n, then you can add.
Yes.
This is binary.
But if it's difference, if
this no. Okay. This you cannot multiply even. Cannot even multiply. Add, yes. Because n by n is n by n. Okay. Matrix, yes. Under addition. This one you cannot define, it's undefined. N by n is okay. Ayn, one more from you. One is like this. Right? 2 positive integers. When you subtract, you probably don't get a positive integer. Like you take 2, you take 3. 2 minus 3 is -1. It goes out. So this is not a binary operation under Z plus. You have to be taking 2, do the binary operation, goes back inside. Okay, cannot go out. This one, it becomes not integer, it's a rational number. This, it becomes negative, not positive. Okay, Ayn, you understand now? If you understand, you give me 1. 1 here and 1 here.
Prof, can I give a group?
Group is already a binary is close. Let me see. If you have, you can define like this also, Ayn. Like this. Okay, it's a power. This is not necessarily be, well, this is okay, right? For integers. If this is integer, oh no, positive integer is okay. For positive integer is okay. But for integer, it's not okay. Like 2 and -3, right? 2 to the -3 is 108, not anymore integer. So you have to erase it. Okay. And any group is defined to be using binary operation. That's why I said it's cheating if you take group. All right, okay. Group action. Okay, now a group action, you have to have a set and a group. Okay. And action star of G on X. So we say G X on X. That's the word. It's a map from G cross X to X. Just now we have G cross G to G, right? So here is G cross X to X. Then it has to satisfy this, such that E star X is X. The action of the identity to X does not change X. Second one, if you take two elements of G, you can have a multiplication. If you act on X, this is equal to act first, the G2 act on X first, and then there's a star here, right? Missing a star. First, this means you take the multiplication of the element G1, G2 in G, you get one element, call it G, you act on X. This one, you take G2 first, act on X first, you get something in X. Then you take that and act G1 on that. They are equal. They're supposed to be. Okay, and we call this X is a G set. Okay. All right. I want you to go through the example and find one more different example. And you show me in the next class. Write out or type and put in the reference, which reference that you get. Not the one example in this, but you can come up with your own. I want to see that you can come up with one example of a group action. Okay? And go through the last section, which is the orbit.